Hello, so today we will discuss something about the directional derivative and the use of the gradient. Let us just get things started. Okay, first we will see what is a directional derivative. Again, I will use the same example that I had given the other day. You are having this metal box. Imagine that it is made up of metal. You can heat this box, okay, but the heat is not evenly distributed. Okay, the temperature at this point, it will be different from the temperature at this point. Okay, similarly temperature at this point will be different from here. Okay, what I want to do is I want to calculate the change on moving from this point to this point along this line. Okay, so what I want to calculate, what is the change in temperature at this point along this line. Okay, that is the directional derivative. So this is exactly what I had written, that f be a scalar function of three variables. I had taken a scalar function, okay, just like temperature, it is a scalar function. Okay, the directional derivative of f at p along a line PA is given by this limit. Okay, so exactly why are we defining it in this way? Because if you remember, if we have to calculate the change, we want an instantaneous change. By instantaneous change, I mean to say that A and P should be very close to each other. Okay, A and P should be very close to each other. That is why I am having this limit. A approaches the point P. Again, we are calculating the directional derivative of P of f at the point P along this line PA. Remember that if you have to calculate change, the change, it will be the final minus initial divided by the length. Okay, so that is exactly what I'm writing over here. But to get the instantaneous change, I am putting A tends to P. Okay, so A should be very close to P. So we will get an instantaneous change at this point. Okay, similarly we can calculate the directional derivative along PB. Okay, we just have to replace A with B in this limit. Okay, so this is how we do it. Okay, but since calculating it by using limits like this, it may be a bit complicated. That is why we have a theorem how to calculate this one, and that is by the use of directional derivatives. By the use of the gradient. We will use the gradient how to calculate the directional derivative. Let us just state this theorem. Okay, the directional derivative of f at p along the direction u cap, okay, along the direction u cap. If you remember, this is a unit vector. It specifies the direction is equal to gradient f dot u cap. Okay, so over here, what is u cap? Okay, you can even think of it in this way. PA, it is a vector, so PA divided by its magnitude PA. Okay, this one will give you the unit vector PA. Okay, so again, this one specifies the direction. Okay, let us, we don't need a proof for this theorem. Okay, if you want a proof, I will hand it separately. Okay, but for now, let us just take a look at the exercises. So this is the first application of the gradient, that is to calculate the directional derivative. Okay, find the directional derivative. Okay, you can just make up any function f, x, y, z. I am writing f, x, y, z instead of f, just to denote that f depends on x, y, and z. Equal to, okay, we can take any function, x cubed y plus xyz minus x y square z cubed Okay, let us just take this very simple looking function. Again, it has to be a scalar function. So find the directional derivative of the scalar function along the vector let us just make up a vector 3i plus 2j minus k. Okay, so we will use this theorem, but we have to be very careful because this one should be a unit vector. Okay, so let's see. Solution. So over here f is equal to x cubed y plus xyz minus xy squared z cubed. So first let us calculate gradient f. Okay, maybe we can even along the vector at the point. Okay, because whenever we are talking about derivative, we have to even specify the point. So at the point 0, minus 1, 2. Okay, let's see. Okay, maybe 3 minus 1 point and 2. Okay, so let us calculate the gradient. The gradient is equal to del f del xi plus del f del yj plus del f del z. Okay, I will just write here, okay, in case u bar, it is this vector 3i plus 2j minus k. 2j minus k. Okay, I will keep that in mind. Okay, because now I will have to erase it. 3 minus 1 and 2 as well. Okay, so now let us calculate this gradient. So del f del x, differentiate this one with respect to x, this whole thing. Differentiate this whole thing with respect to x. So y over here it can be taken as constant. Differentiation of x cubed, it will be 3x squared. Differentiation of x partially with respect to x. Okay, y and z, it can be taken as constant. And differentiation of x will give you 1, so I'm not writing it down. Similarly, over here will be y squared z cubed I. So this is just del f del x plus del f del y. This is y. Differentiate this one with respect to y. X cubed, differentiation of y, it is 1. So plus xz, they are constants. Differentiation of y will give you 1. And over here you will have minus 2x yz j and plus del f del z k. Del f del z. So differentiate this one with respect to z. Over here we will be getting 0 xy, and then over here we will be getting minus 3xy squared z squared. So this is the direction, the gradient. Okay, now u bar, it is equal to 3i plus 2j. The direction is this. So now first we will need a unit vector, will be 3i plus 2j minus k divided by square root. Square root 3 square will give you 9 plus 4 plus 1. Then 14. 3 by root 14 plus 2 by root 14 minus 1 upon root 14. Okay, so this is what we are having. So now we just take the dot product, which is the required directional derivative. Therefore, the required directional derivative is equal to grad f dot u cap. Okay, so what we can do over here, instead of I, okay, just take the dot product of this one with this one. Okay, we can easily do this one. 3 by root 14, instead of I, just write over here square root 3 upon 14. 3 by root 40 plus, instead of j we can write it with, okay, just take the dot product, you will be having this, and k will be minus 1 upon root 40, minus 1 upon root 40. Okay, so this is the required directional derivative, which is equal to this, grad f dot u. You will be having this. But now we have to calculate it at a point which was given to us at p equal 3 minus 1, 2. Okay, the directional derivative is equal to, so just replace the variables here. Okay, y it is equal to minus 1 minus 3x squared, 3 squared will give you 27 plus yz will give you minus 2 minus y squared it's 1, z cube it is 2 cube minus 8 plus x cube again will be 27, xz plus 6 minus 2xyz to 3, 6 to 12 plus 12, 2 upon root 40, and similarly this one you can calculate it to be x, okay, x will be 3 minus 3, 3xy squared, 3x will give you 9, 9, 4, 36, minus 36, minus 1 upon root 40. Okay, I hope it is clear. This one is minus 1 upon root 40. So this is the required directional derivative. Now all we have to do is simplify it. 29 minus 37 times 3 upon root 40 plus 27 plus 17, 27, 33, 45, 45 times 2 upon root 40, and this one it's equal to minus 39. But with this minus 1 you will be having plus 39 upon root 14. So overall the answer will be upon root 14, 3, 7, 21, 29 minus 101 minus 111 plus 90 plus 39. 90 plus 39 will give you 14, 91. Okay, so this one will be the required answer, 18 upon root 14. Okay, so this is again a very simple exercise. All you need to do is you just need to remember that the gradient, it will give the gradient dot the direction will give you the directional derivative. Okay, this is a very simple exercise. So now let us take a look at another important application of the gradient, which is in finding normal vectors. Okay, again a theorem. The gradient of f at a point P gives the normal vector at P. Okay, so this is a very easy exercise, a very important theorem. Okay, but we will do a very easy exercise. So what this one is saying, if you remember that if you are having f, then it will be a surface. Okay, so something that looks like this. Okay, it can be any surface. So it's not looking very nice. Okay, so this one, it is a surface. Okay, it can look like this. So the gradient at f of f at a point P, so just take any point P on this surface, then the gradient it will give you the normal vector. Okay, so if this one is the surface and P is somewhere over here, then the gradient of F gives you the normal vector of that surface at the point P. Okay, let us just do an exercise. Find the normal vector of the surface fxy, okay, of the surface fxy. Okay, let us make it as a function of two variables. It doesn't really matter if we have two or three variables. Equal x, y minus xy plus y. Okay, let us find the normal vector of the surface fxy equal this one and the point at the point 1, 2. Okay, so let's see. Solution. We will have to write this one. Grad f gives a normal vector. Okay, so now f is equal to this one, x squared y minus xy plus y. Now we just have to find grad f del xi plus del f del yj plus del f del z. Okay. Okay, so this one, it will be equal to del f del x. Differentiate this one partially with respect to x. You will be getting 2xy minus y. Differentiate this one partially with respect to y. You will be getting x squared minus x j. Differentiate this one partially with respect to z. You will get 0 plus 0. Okay. Okay, so at the point P, grad f P, I forgot the point. Okay, at the point P, okay, I forgot how much was the point that I had given. Okay, let us just take, okay, maybe 1, 2. Okay, just make some corrections. Okay, let us take the point P equal 1, 2. Again, I forgot how much was it equal to. How much was the given point? Okay, at the point P, 1, 2, gradient f. So instead of x, replace with 1. Instead of y, replace with 2. So you will get 4 minus 2i plus x squared will be 1 minus 1j. So will be 2i. Okay, so therefore required normal vector is equal to 2i. Okay, so this is a very important exercise and a very important theorem indeed, that the gradient gives the normal vector. So now let us do another exercise or another application of the gradient. Okay, I will state it here. The angle between two surfaces, the angle between two surfaces is the angle between the normals. Okay, so if you want to find an angle between two surfaces, just imagine, okay, you have one surface and it intersects another surface. If you want to find the angle between them, you just have to find the angle between their normals. Okay, so let us try an exercise. Find the angle between f equal x square plus y square plus z square x equal 0. So if it is a surface, you just set it equal to 0. And another surface f2 equal x minus y plus 2x equal 0 at the point 1, 2. Okay, so how will we do this one? You just remember this node. Okay, so we are given two surfaces. Now we just have to find their normals, and then we find the angle between the two normals. Okay, solution. The normal vector. I think it is best if we find this one. Since we have to find the normal, so first of all we will have to find the gradient. So first let us find grad f. Grad f, f1, it is equal to del f1 del xi plus del f2 del xj plus del f1 del xj. Since we are finding grad f1, so everywhere over here it is f1, f1, f1. Sorry, this is del y, and this one is del z. Del f1 del x. Differentiate this one partially with respect to x. You will be getting, forget about this 0. So you will be having 2x plus z squared I plus del f1 del y. Differentiate this one with respect to y. You will be having 2y j. Differentiate this one with respect to z. You will be having 2zx. Okay. So now that we have find gradient, now we can find the normal vector. Therefore, normal vector at 1, 2 of the surface f1. Of the surface f1 is, let us denote it with n1. Okay, normal vector, let us denote it with n1. So will be equal to, just substitute 1 and 2 over here. Okay, maybe 1, 2, 3, since now we are having 3 variables. Okay, 1, 2 and 3. Okay, so over here we will be having 2 plus 9 will give you 11. You will be having, okay, let's write it. 2 plus 3 square will give you 9. 2y, it will give you 4j plus 2zx, 6k. So this is the normal vector of the surface f1. So this is the normal vector of the surface f1. Similarly, we can find the normal vector of the surface f2. Okay, so let's see. So now we don't need this part anymore. Now what we can do is we can find grad f2. So everywhere replace it with f2, f2, f2. Let us just write that one. Del f2 del x, del f2 del y, and here it will be del f2 del z. Okay, so let's find it. How much is it equal to? Differentiate this one with respect to x. You will be having 1 minus y squared plus 2y. Differentiate it with respect to y. You will be having 0 minus 2yx plus 2x. Differentiated with respect to z, you will be having 0. over here should be k. Okay, so this is what we are having. Similarly, we can say, okay, I will keep this one. After this part, you can write this. Therefore, normal vector at 1, 2, 3 of the surface F2 is, we will denote it with N2. So over here will be 1, y square will give you 4, 2y will give you 4 again, I, plus minus 2yx minus 4 plus 2x plus 0k. So this is what we are having. Will be I minus 2j. Okay, but if you remember the question, it asks us to find the angle between the two surfaces. Okay, so the angle between the two surfaces is the angle between their normals. So this is exactly what we can do. Okay, so now n1 dot n2 cap. Remember, this is a very important line. Since we want to find the angle, we will use the dot product. The angle between the two normal vectors, it is given by the dot product. It's given like this: n1 n2 cos theta. This one all of you know, the dot product is given by this formula, but we are using this one to find the angle between the two surfaces by using the normal vectors n1 and n2. So n1 dot n2, you can see 11 times 1, it will give you 11 minus 8. The magnitude of this one will be square root. N1 will be 11 square plus 4 square plus 6 square. Magnitude of this one will be 1 square plus 2 square cos theta. Okay, so now we are done. 11 minus 8 will give you 3. So this one will give you 121, 16, 36, 12, 13, 3, 4, 5, 4, 5, 6, 7, 173. Okay, and this one will give you 5. Cos theta will be 3 upon square root 5, 3, 15, 5, 7, 35, 36, 5, 6, 7, 8. Okay, so it's looking a very complicated number. Okay, but doesn't matter. The angle, we can just write it as cos inverse 3 upon root over 865. Okay, we are getting such a ugly looking number because I just made up the question on the spot. But that is exactly the beauty of it. Okay, you can use this result for any type of surface that you like. One particular example that you can use this formula is when you calculate the angle between two planes. Okay, so a plane is also a surface, right? So maybe you can try one of this as an exercise. Find the angle between the planes x plus y plus, x plus y plus z minus 1 equal to 0, and 2x minus 2y plus 3z plus 5 equal to 0. Okay, so you can try this exercise by using the gradient. You can even mention a point at P1, 2, 3. Okay, so you can find the angle between these two planes just by using the gradient. Just as a hint, you can set f1. F1 will be x plus y plus z minus 1, and f2 will be 2x minus 2y plus 3z plus 5. And then you can follow the similar steps, then you can find out the angle between the two planes. That is all for today.